Hey everyone, back again for our next lecture video, which is going to be on Chapter 3, Earth Materials. And we're going to get into a little bit today about rocks, the different types of rocks, the rock cycle, a little bit of chemistry. I'm going to tell you up front before we even get into this that I am not a chemist. I really haven't studied a lot of chemistry since my days when I was about your age. I don't, you're going to find when you get into your life career, so you're going to study certain things in school, no matter the discipline, whatever it is, unless you're like something like a nurse or something like that that actually does stuff every day, there'll be certain components that you study that you won't think about again for a long time. In my field, what I do a lot of field work. I run a lot of programs. So there are certain aspects of things that I study that I still do use all the time. I'm one of the few people in my circle of friends that actually does use a lot of my education in my career. But there are parts of it that I haven't even looked at since then. So just an honest disclaimer there. I have to kind of go back and look at some of this stuff again before we even jump into it. So the chemistry side, what I want you to get out of that part of it is I just want you to have a very basic understanding of how these things are composed in the beginning, what their basic foundation is. I'm not going to test you a lot on your knowledge of chemistry. This isn't a chemistry course, but you do need to know the basics of what we're doing. So you probably had this in high school, in your high school chemistry class. Most people, I think, take a high school chemistry class. At least we did when I was in school. So the basic building blocks, you're going to have your atoms with a nucleus, your protons and neutrons, and then the electrons circling the nucleus. And those will form into elements. So elements are atoms with the same number of protons, and they will come together, form molecules, form into elements. This is a general diagram of how that works. Your proton, your circling electrons, the positive charge of the nucleus, the negative charge of the electrons is what the bond, that's what attracts them to each other and keeps them in a stable state. So when we have an atom, we can have different types of the same atom. For instance, here you have hydrogen. The typical hydrogen is just a proton with an electron. Deuterium has a proton with a neutron and electron, and then tritium has two neutrons. So that's just showing you, I don't expect you to remember that. That's just showing you that even though it's the same element, it can vary just a little bit in its structure. So when we start applying this to what the Earth is actually made of, that's why we need to know those basic building blocks, because there are certain materials that make up our planet, the Earth. As you can see here on the left, you have a cross-section of the Earth, and you can see the four major parts of the interior of the Earth. Some people say there's three. You have the core, but it's split into the inner core and the outer core. Then you have the mantle, and then you have the crust. So for all intents and purposes, what we deal with is the crust. Now, as you're going to learn in this chapter, the core and the mantle have large roles to play in how this planet has evolved and what it is today. And it still is active. Even volcanic activity, plate tectonics, depends on what's happening in that core. However, as human beings, what we see and what we deal with on a daily basis is going to be pretty much strictly that very thin layer of crust that we see on the very outer edge. The smallest of the zones by far, but it's also the habitable zone that we interact with on a daily basis. So that's just a little background on how the Earth is made inside. On the right, you see a pie chart. There's two of these actually. The top one is the elements that we find most commonly in the crust, which is what I just said. The very outer shell of the Earth, that's what the plates are. the top of the plates that scoot around on plate tectonics that we're going to talk about in the next chapter. And then the bottom pie chart is the elements found in the entire planet. So that includes the mantle and the two cores, the inner and outer core. So as you can see, silicon makes up a large percentage of both of those. Oxygen does as well. But you see in the whole Earth, when you get into the cores, you see a lot of iron, which on the surface you don't see quite as much iron, a very small amount compared to the core. Magnesium is also a major player here. So that just gives you a little bit of the background of the elements that we're dealing with within the Earth. So minerals are naturally occurring. First of all, they are inorganic, which means they have never or will never, they don't have anything to do with life or carbon. They form a crystalline structure. They may be one or more element, and they have a definite pattern of how they are structured. What you're looking at here on the bottom, sodium chloride, that is more commonly known as salt. You see the chlorine atom in the middle and the 6 sodium atoms on the outside. And the crystalline form that they are creating there to stay bonded together and keep that crystalline form. So when you have a mineral, you're going to have a continuing crystalline form. It's going to be the same throughout that mineral in a setup similar to this. It might not be exactly like this, but it's going to be uniform just like this. So we know of over 4,000 minerals. Each of those has a unique chemical and physical property, and this is what makes rock. That's when we look at rocks, this is what's in rocks, these minerals. And again, just like the atom that we looked at earlier, the hydrogen atom, these minerals can have different structures as well, depending on how they're set up, how their bonds work, how they were formed, the heat and pressure they were formed under. In this example right here, this is simply carbon. Now, carbon that has been exposed to very high heat and very high pressure can take on a crystalline form that makes a diamond. Most of you are familiar with diamonds. But also, if you think of an old school pencil, the lead in the pencil, that's graphite. That is the exact same material that a diamond is. It's no different other than the structure of the crystalline makeup of that mineral. The bonds are different. It was formed under a different environment. Therefore, it has bedding planes in it that shear off really easily. And that's why when you scoot it across a piece of paper, it leaves a dark mark behind it, because those layers of atoms are shearing off from that graphite and staying on the paper. So again, carbon, two very different types of solid structures, but the same material. Silicates is another class that is very common within the rock world. Again, I'm not going to get into a lot of detail on these charts. I just want you to understand a silicate is silicon and oxygen. There are several different structures that these crystals can take to make up different types of rock and different types of minerals. So, rock forming minerals, we have 12 that are the most common. You're going to see different names of these. You'll see these in your book. I'm not going to spend a lot of time on these. Just know that when you see certain words like ferro, you see in the second bullet point there, ferromagnesium silicates. We just saw the silicate is silicon and oxygen minerals. I'm sorry. And ferromagnesium refers to ferro. Whenever we see the adenosine at ferro, that means iron. So you can have a rusting effect. If you see a sandstone that might have some iron in it, you might see it a reddish color. Magnesium, of course, is magnesium. So that's an iron magnesium silicate is basically what that's saying there. So again, I'm not going to get into deep detail on the chemistry, but do read over that. I'll have a few questions in your assignments on that. I just want you to have a basic understanding of how these are structured. So now we're getting into the rocks. So when we talk about rocks in geology, we talk about three primary types of rock. And these are the three types: igneous, sedimentary, and metamorphic. And what I want you to understand while we start to go through these different types of rocks is the rock cycle. So we think of rocks because I mentioned this in our last lecture. On a human time scale, and even the human race time scale, is just a second in the whole geologic time scale. So when we talk about time scales, we have to think about, okay, are we talking about earth and rock time scales, or are we talking about human time scales? So we're talking about the geologic time scale here. And when we think about that, we're thinking about millions of years. And the reason I'm bringing this up again is because we have what we call the rock cycle. So we have these three different types of rocks, and we're going to be talking about how these are all formed. But keep in mind that this is a cycle. It's a circle of material. It's made. They're broken down. They're reintroduced into the cycle and recycled into a different type of rock sometimes, because the earth is in constant motion. And even though on a human time scale, we're not going to see hardly any of that, when we see a piece of limestone sitting in our driveway, it's going to be there for our lifetime. It's not going to go anywhere. But when you're talking about millions of years, these rocks will break down over time, and they will be reintroduced either as another type of rock. Maybe they're close to a boundary on a plate in plate tectonics. They might be incorporated back into the internal part of the earth. So we're going to go through this, and I just wanted you to get that, to wrap your head around that time scale that we're talking about. So igneous rocks. So what I want you to think about igneous rocks, this is kind of the starting rock. I think of it in my head, because igneous rocks are made from melted material in the Earth's core and up through the mantle, up to the surface. So this is actually molten rock that has cooled down and become solid. So think about a volcano. Everybody has a mental picture of a volcano. So what comes out of a volcano? Well, that red liquidy stuff, that's called, if it's inside the earth, it's called magma. Once it breaches the earth's crust, we call it lava. Basically, it's the same thing. It's just where it's located. That's melted rock. That is so hot that it melts these minerals, and it can either destroy them and bring them back into the magma, or most often, by the time we see it happening, it's actually adding rock. It's making new rock, because once that lava comes out of the ground, out of the volcano, and hits cooler air or cooler water or whatever the case, it's going to start to cool and solidify. So we have two different types of igneous rocks: extrusive and intrusive. Here's the difference. It has to do on where they're formed and where they cool down to become a rock. Extrusive, think of the word external. External means outside, right? So once that lava leaves the volcano, it hits air or water, and it's cooled rather quickly. So extrusive means it was formed on the surface somewhere after it's come out of the earth. So those are going to be typically very fine grained, because if they cool really quickly, those crystalline structures don't have time to consolidate as much. So you think of obsidian, which basically looks like glass when it cools. That's a fine-grained extrusive igneous rock. Intrusive, on the other hand, is when you have this magma under the ground, and maybe it breaks away from the rest of the magma, and it just sits underground. And it takes it a very long time to cool down, but it does cool down and eventually solidify into rock. That's intrusive igneous rock. and it's going to be more coarse grained because it's cooling very slowly, and that allows the crystalline structures to form more heartily. So you're going to be able to see that crystalline structure in there a little bit better, and that on the right is what we see in granite. So those are the different types of igneous rocks. Here's just a photo of that. When it's into the ground, it's called magma. Once it leaves and gets to the surface, it's called lava. And you can even see in this picture here, the way it's cooling. This is a pool of lava here because it's on the surface, but you can see it looks like there's cracks, the red cracks. That's actually where it's cooling when it's hitting the air, and it's forming rock like a crust on top of that lava. And these are just cracks that have formed where it's still escaping. So that's basically what you're looking at, is how land on Earth first began. Here's a chart. This is in your textbook. Again, I'm not going to go into a lot of detail on this. This is giving you some of the minerals that we're talking about: the iron, magnesium, calcium, sodium, potassium, and silicates, and it's just a spectrum of where these different types of rocks are forming. These igneous rocks are forming either on the surface or underground. Now we're going to talk about weathering, because this is going to lead us into our next rock type. So when you have a rock in the environment on the crust where we're located, it's exposed to weathering. Weathering can mean different things. Weathering can be from heat, like if it gets really hot outside. It can be from cold. As you know, materials either expand or contract depending on temperature and structure. So when something gets hot, it expands typically. When something's really cold, it contracts. So when you have rocks that naturally have cracks in them, and you have a 100-degree day, but it drops to 30 at night, that happens in some deserts. Really hot to pretty cold, that expansion and contraction can further crack those rocks. In addition, if you have cracks in rock, say even here, and you have that crack gets water in it. Say it rains, and that night it gets down to 20 degrees. Well, that little bit of water in that crack's going to freeze. And when water freezes because of the changes in the structure of the molecules, that actually expands. So that it's called frost wedging. That means water gets in cracks, freezes, and expands, and that makes that rock crack or break more. Other things like plant roots can grow in the cracks and expand the rocks and push them out and make them crack. Some chemical crystalline growth can happen in some rock layers, but that's one way that we weather rocks, and they start breaking down. And there's a point to this as we go through this, because as these rocks start to break down, the more they break, the smaller pieces there are, and it makes it easier because there's more surface area to further break down and break down and break down until they break down to the point where once was a consolidated rock, might be sand, the little particles of sand. It breaks down to that level. Another type of weathering that breaks down rocks is chemical. So you have certain chemicals, as we've already discussed, in these rocks. And certain other chemicals might react with these chemicals that are already in there to enhance the breakdown of the rock. Now, one is oxidation and reduction. And I'm just going to mention that because, and you're going to find as we go through this, I'm going to focus on what we have here in Kentucky more, since we're more familiar with this, and I work with this a lot more, so it's more familiar to all of us. So oxidation reduction, oxidation is a chemical reaction with iron particles. And you all know what rust is, right? So you've seen rust on a car or on some piece of metal somewhere. That's oxidation. And that's why it's red, because it's iron. So some layers of sandstone here in Kentucky have higher concentrations of iron in the rock. So sometimes when you see those in nature, if they're damp or moist, they look like they're orange in color. That's oxidation. So that's actually breaking down that rock very slowly, but it's breaking it down. Another thing is chemical dissolution. And this is one that we're really going to discuss in more detail, because if you look at the tombstone on the right over there, that's a limestone tombstone, and you can see that's probably, I can't read the date on it on this little screen, it's probably a couple hundred years old at the oldest, probably younger than that. And it's already degrading from the elements. So limestone happens to have a lot of calcium in it. Makes it a very basic type of rock. Basic on the acidity scale, not basic simple, but on the acidity scale it has a basic consolidation. So all rainwater is slightly acidic. Sometimes more than others depending on the pollution that we put out there, but all rainwater is slightly acidic. So acid attacks a base, and it's trying to equal out to become neutral. So it'll dissolve that rock slowly. And I mentioned that's so important here, because that's what's happening that makes all the caves and the sinkholes and all that in our area. We're underlain by limestone. That water is getting in there. It's chemically dissolving that limestone because it's slightly acidic, and it carves out those caves and those sinkholes and those vertical shafts. And we're going to be talking a lot more about that as the semester goes on. I'm skipping over this slide. Okay, so now we're to sedimentary rocks. And as the name states, they're made of sediment. So it's compacted and cemented together. So what is sediment? So going back to that weathering, that's why we talked about weathering before we talked about sedimentary rocks. So remember I told you the big rocks become smaller rocks, eventually they become sediment, which is small particles of rocks, basically. You have sands, you have clay, you have different sizes of these sediments. So these sediments are moved sometimes by wind, as you see in the bottom photos. So most of the time by water, especially in our area, it's water that carries these sediment, and they deposit them in different places. Now usually a sediment, depending on its size, so the bigger the sediment, the less it moves in water. The finer, the smaller the sediment, the more readily it moves through water. So that's important, because depending on where that sediment falls out and stays, that's where it has the potential to make a rock layer at some point in the future. Now, not all conditions are conducive to that. Typically, that's going to happen at the bottom of your lakes and oceans, where the water is still, and over hundreds of thousands of millions of years, this sediment piles up and piles up and piles up. And we get layers, vertical layers of sedimentary rock. You can see that in any road cut. When you're driving down the road next time and you go through a place where they blasted out the sides and you can see the rock, look over and you'll notice, if you've never noticed before, there's distinct layers. You can see different layers. That's different layers of sedimentary rock. In our case, it's limestone. So there's two types of sedimentary rocks. There's detrital and chemical. So detrital, think of that more as just kind of deposited layers. So you have something like sandstone. You have physically sand particles that has been transported to that location, probably by moving water at some point. It could be by wind, but typically moving water. And over the hundreds of thousands of millions of years, it's piled up and piled up and piled up. There's certain chemicals in there that will assist it under pressure of all that weight. It'll consolidate into a rock. So sandstone, it looks exactly like you would think sandstone would look. It's a rock, but it's really grainy. You can actually kind of see the grains of sand in it. Shale is similar, but it has a lot finer grains. It's more of a mud. There's actually a mudstone. Shale actually is a little bit smaller particle size than mudstone even. So you can see those different detrital layers. So where you're going to get those kind of depositions are going to be near the coast of an ocean, or maybe at the bottom of a lake, where you have a lot of water moving this sediment in and piling it up pretty quickly, typically. I'm talking about pretty quickly over geologic time, not our lifetime, but geologic time. Now the chemical sedimentary rocks are similar, but a little bit different. So chemical, we talk about limestone, and that's what we have here. So limestone, we call it chemical. It's also kind of deposited in the same way. You have sediment that's moved and it's layered on top of each other, and that pressure eventually kind of compresses it. But there's a lot more of a chemical process going on in these layers. And typically, that has to do with the environment where this is happening. And I'm going to go ahead and go to the next slide because this will help us a lot understand this. This is a very, very good diagram right here because this is showing what's happening. Up here you have the rocks, probably old school igneous rocks at some point. They're eroding, the little fine sediments being carried down in rivers and streams, and it's going out here into the ocean. So you see where I talked about the sandstone. You see here it says sandstone. Areas like this, probably out a little bit further than what this is showing, is where the environment would have been for sandstone layers to accumulate. The sand, you see sandstone, you see siltstone, you see clay shale. So the reason that you see these different ones at different distances from the beach is because sand is a bigger particle than silt, and silt is a bigger particle than clay. And remember, the water only has a certain capacity to carry these particles. The heavier the particle, it falls out sooner in the water column. So your bigger particles are going to fall out earlier. So up here you're going to have big rocks. As you go down, the sand might make it to here and it's going to fall out. The silt might carry on out here a little bit further and then fall out. So that's why you have different places these accumulate at different rates, is because the capacity of water to move these. So out here in this area is where you're going to start to get your limestone. If this is an ocean, I'm going to see what the next slide is. Okay. So if this is an ocean, and here in Kentucky, I'm going to go ahead and tell you a little bit about the formation here. This part of the continent was underwater about 320 million years ago. That's how long ago this rock that we see around us every day was formed. So we were under a shallow, warm water sea. Think about off the coast of Florida today, a similar type of sea to that. Not really deep, but deep enough it had a lot of coral, a lot of sea life. That coral, that sea life, the crustaceans, the invertebrates, they use calcium a whole lot in their shells and their exoskeletons, in the coral itself. And that abundance of calcium settles out into these layers as they're put down. And that calcium, over time, with pressure and time, kind of concretes all that sediment together. So that's why we call it more of a chemical type sedimentary rock, because it's actually kind of cemented together from all that calcium. And that's why first of all, that's why the rock, I said it was basic. The acid eats away at it because it has a high amount of calcium in it, and that acid will eat away at that rock. And also, you can find lots of fossils here in our area. I could take any one of you out to a creek, a Barren River lake bed in the winter where the water's down. You can find fossils everywhere here. And that's because we were on the bottom of a warm water sea. Now, different limestones sometimes are a little bit different. If you zoom into this limestone, you don't see a lot of fossils, but you can see the grains in there when you put it under a microscope. Looking normally, it kind of look like gray rock. When you zoom in, you can see the particles that are actually there, and you can see that cementation in between those. That's that calcite. Sometimes you see a lot more fossils just openly in the rock. It depends on the environment and how fast it formed, different factors as far as what fossils you may see or what the composition of that limestone is. Some limestone is very tightly packed, very dense, like this sort of is right here. Sometimes it's more like this with a lot of fossils and maybe not so tightly dense. It formed a lot more rapidly than something like this would have formed. And again, this slide kind of talks about what I was saying about where the different particle sizes fall out and form, and the environment that you would have seen on the bottom of this ocean. And again, here we have just a couple of pictures illustrating the different types. Now, one thing to keep in mind, we're going to talk in the next chapter about the plate tectonics and these earth processes. Sometimes you're going to find these sedimentary rocks way up on top of mountains. You might think, how did they get all the way up here? There's no way they formed on the ocean or under a lake bed or something up here. Well, they've moved there. They've been pushed up there, and we're going to talk about that a little bit later. So the next type of rock we're going to talk about, the last rock, we've talked about igneous, we've talked about sedimentary, now we're going to talk about metamorphic. Metamorphic rocks are basically either igneous or sedimentary or other metamorphic rocks that have undergone some kind of physical or chemical change due to heat and or pressure. So this is a good example of this. You see there was existing rock here already, and maybe you have something like a magma chamber that develops, that comes up and encroaches on the surface if you're near a plate boundary, and it gets up into this shale or limestone, and you start to have a tremendous amount of heat and pressure. Now, it doesn't get hot enough to remelt it. If it remelts it completely, it becomes a new igneous rock. But if it gets hot enough to kind of think about just cooking it, it gets hot enough that it can actually reorganize the crystalline structure a little bit, but not completely melt it. Think about baking it. That's kind of what it's doing. Add to that pressure, and when you put those together, heat and pressure together make a far greater force than one or the other separate. A good example of that, and you all are probably too young to remember this. Some of your mothers may use them. A pressure cooker in the kitchen. They make them as a standalone machine now. Back when I was young, we actually had a pressure cooker that you sit on top of the stove, and it releases gas, air and gas as it cooks. Because what it does, it increases the pressure inside and heats at the same time. And what that does is that creates a tremendous cooking environment without burning it, or in this case, melting it. So that's what's going on with metamorphic rocks. And certain types of rock change into a certain type of metamorphic rock. For instance, limestone, if it gets some metamorphic actions on it, turns to marble. You might have seen marble in ancient Rome. They used it a lot for their statues and their buildings. Shale becomes slate, and so on. So that's what a metamorphic rock is. And I'm not going to go into great detail on that because we don't have it around here. But you can kind of see how it can reorganize the crystalline structure without completely melting it. That's why you see the striations in the rock form instead of just a general kind of a mottled effect that you would see in some other rock. So here's the rock cycle. And I want you to pay particular attention to this in your lesson. I want you to study this and understand this. It looks like a lot just looking at it, kind of confusing, but once you understand it, it's very simple. Basically, you start with molten rock, melted rock. It cools and becomes an igneous rock. And from there, you have weathering. It could become a metamorphic rock if it gets heat and pressure, or it weathers and becomes sediment. That sediment becomes sedimentary rocks, and you can see in between here, it jumps between the different rocks. But basically, what this is showing you is this is a circle. This is a recycled circle that these minerals can recycle in the geosphere, in the Earth's environment, over geologic time, and it's a closed system. Now, you might ask, where in the world does rock be able to be remelted? How can rock, limestone here in Kentucky, re-enter the earth and be melted back into igneous rock? And we're going to answer that in the next chapter. So stay tuned. It has to do with plate tectonics and earth boundaries. The short answer to that, though, is you don't have to worry about that as far as our lifetimes go, because this rock is not going anywhere anytime soon here in Kentucky. But over time, over geologic time, it has the potential to be recirculated and get back to that state. And again, we talked about this in the first chapter. We can study rock layers and we can learn about the past and when these layers were formed and what the environment was like in the geologic past. This is a pretty cool slide here. This is sedimentary features on Mars. You know, we have the Mars rovers up there right now. We've learned more about Mars in the last probably 10 years than we knew the entire time before that. Very interesting. It's widely hypothesized that there was once liquid water on Mars. We see tremendous evidence of this in their geology. A lot of their rock layers look just like our rock layers do here. They are sedimentary rocks. Sedimentary rocks can form by wind as well. We know there's wind on Mars even right now. But there's strong indications that there was once water on Mars. We're still trying to find that silver bullet to say for sure yay or nay. But everything is pointing toward that right now. So that is the end of this chapter. Also in this lesson, we're going to have chapter 4. So I will post that lecture here in just a few minutes. Thanks, and as always, if you have any issues, you have any questions, or need anything from me, feel free to reach out via email. We'll get together and get it resolved.